Okay, so section 4.2, more on area. And let's do something where we just plain know the answer, right? So suppose I take the function, let's go with minus 2x plus 2. How about that? So that function goes here like this, so minus 2x plus 2. This is at 1, and that's at 2. And suppose I want to talk about the area of that. Well, it's a triangle. I know that formula, right? That formula for area is the height, 1/2 the height times the base. And so that's 1/2 times 2 times 1, and that's 1, an area of 1. Okay, so that's our area. But let's do it with our approximation method. And so a first approximation, I could get lower and upper bounds here. So if I just make one rectangle there or a rectangle here, it's a pretty bad rectangle, right? There's 2, there's 1. What I see though is that 0, which didn't really help a lot, is less than the area is less than, and here I have 2 times 1. Okay, well, so I know the area is less than 2, bigger than 0. But now I could make, now here's the upper bound, right? I could make these rectangles here. I'll put it over here. I could also make lower bound rectangles by starting there. There's a lower bound, and then of course that one at 0. So my lower bound here, remember this is the function minus 2x plus 2. So that's at 1/2. So I have minus 2 times 1/2 plus 2. Okay, there's the height of that rectangle times the width, 1/2, and then plus 0. That's less than, let's start going with less than or equal to, but less than or equal to the area, less than or equal to. And now this upper one I'll have to put down here because I don't have enough room. Again, see that's at 1/2, but you see we're going to evaluate this first rectangle at 0. So this is minus 2 times 0 plus 2, and then times 1/2, and then plus, and I have this rectangle over here. Okay, that's the same as that thing, so that's minus 2 times 1/2 plus 2 all times 1/2. And so what the heck did we get for that? Minus 2 times 1/2 is minus 1, plus 2 is 1 times 1/2, so I get 1/2, and that's less than or equal to the area. So I know this this one is 1/2. This one is 2 times 1/2, or 1. So the area is between 1/2 and 3/2. So I brought that down. I took that one up. I got a better answer. So now I could do this thing and I could break it into, 3 or 4 parts. Suppose I go with 4 parts. Well, maybe I should make this a little bigger so I can draw it. 4 parts. And the upper value are those 4 triangles. And so I'm just going to write that one down. And of course the other one, we'll look at that in a minute. But at this point I know area would be less than or equal to those 4 things. Well, I had negative 2x, well, x is 0 for that first one, plus 2, and the total width is a 4th. Then the next rectangle is evaluated at 1/4, so that's minus 2 times 1/4 plus 2 times 1/4 plus negative 2 evaluated at a half plus 2 times 1/4 and then finally plus my negative 2 evaluated at 3/4 plus 2 times a 4th. Okay, so there's the upper bound on the area. This is getting old really fast, but as I look at this pattern, you see what I'm doing is I'm taking the sum, and it goes, in this case, I equals 1 to 4, and well, actually, let's not do 1 to 4 because, right, I used a 0 and so maybe the easier thing would be to go from 0 to 3. Again, you're in charge of describing things, but I think that's probably best is we go from 0 to 3, and we can switch it back to 1 to 4 in a minute, but just as we see here, then you see I took minus 2 times I divided by 4. Okay, right? I took 0 over 4, 1 over 4, 2 over 4, 3 over 4. So that was, to me, I decided that was the easiest way to describe what I was putting in there. I goes, so it's minus 2 I over 4, and this is plus 2, and then times 1 over 4. Okay, so that's what I did. Now I can change that thing a little bit. I could just say, well, instead of trying to come up with this, what exactly those numbers are, I could have just called this like an x sub I and said, this first one was x0, the next one was x1, x2, x3, something like that. And so there is a way to do it. Another way, if I wanted the sum to start at 1, well, I can do a change of variable, and so this one was the easiest way for me to kind of write it down. But suppose I wanted to start at 1. Well, so I could say, well, let's let j equal I plus 1. Then j would start at 1, right? Because if I equals 0, you get j equals 1. But then it would stop at 4, because if I equals 3, j equals 4. And so I could actually make that sort of substitution. So if j equals I plus 1, then j minus 1 is I, or I equals j minus 1. And I can just switch everything out in here. Okay, so I could make that a sum j equals 1 to 4. Okay, and I got that from doing these. And then minus 2, and I just make my substitution in there, j minus 1 over 4 plus 2, and then all times 1/4. Okay, so either of these describes that upper bound. The area is there. Now, actually, again, I like that one better. Your textbook, I think because I don't know, they're afraid to go from 0. I don't think I see anything in the textbook that starts at 0. You know, this is some of the stuff I just don't like about a lot of textbooks, is that, you know, they, I think they sort of, in a way, make things harder than they need to be by trying to shelter you. You know, it's okay to start a sum at 0. Okay, so we could go with either of these. So let's continue with this on another page. And so in general, as I'm trying to find this area, what I can do is I can just start adding more and more of these, and we'll try to come up with our nice summation formula for what we have there. And so, see, if I call this one x0, x1, x2, x3, x4, x5, then what I can see is my lower bound Okay, so I drew those 1, 2, 3, 4, 5, 6 rectangles. Now the sixth one is just a 0, but so my lower bound, what I'm doing in general is, so lower bound, what I'm doing in general is I am summing from I equals, now I'm going to start here, oh, no, I'm not. I'm going to start here, right, because there's the height of the rectangle, and I'm going to go march through each of those. So I equals 1. Now I'm going to change this last one, well, actually, let's see if I line them up. There was an x5, and actually that endpoint there I could call x6. So I am going to march up here, but I'm going to call that last one n, and this one here n minus 1, x n minus 1. So I'm going to do this one at x1, x2, x3, x4, x5, x6, or in other words xn. And I'm going to evaluate minus 2, not xn, xi, plus 2. And then, since this went from 0 to 1, the width of each of these is 1 over n, right? Because there's 1 interval, 2 intervals, 3 intervals. It ends here at n. So this is a nice thing about calling this first spot x0 and so forth. I get a pretty nice formula here. So x sub I, that's 1 over n. So that's my lower bound formula. And, you know, I could actually add this up a little more by putting in what these values are, right? So this is, this first one here, this is 1 over n, then 2 over n, and so forth. So I could actually rewrite this as the sum I equals 1 to n of minus 2 times I over n, like that, and then plus 2, and all times 1 over n. And now, if I split this thing up, I can, so again, we're working on the lower bound. I can write this as, well, first let's send through the 1 over n. So I have, or actually, let's take out the 1 over n. So I have 1 over n times the sum I equal 1 to n of minus 2 I over n plus 2. But now I can write that as two different sums because I have a plus there. I'll just break apart the sums, rearrange, and I have 1 over n, and so I have the sum I equals 1 to n of minus 2I over n, and then plus the sum I equals 1 to n of 2. So that is 1 over n. Now this, negative 2 is a constant, n is a constant, so I get negative 2 over n times the sum I equals 1 to n of I plus 2 times the sum I equals 1 to n of 1. I can evaluate those. So this is 1 over n minus 2 over n, but then remember the sum from 1 to n of the numbers, so I equal 1 to n of I there, is just n times n plus 1 over 2. So see, I can actually tell you what that is. And then this one is just 2n. So as I look at this, I can do some simplification here and there. And so this is 1 over n times, oops, quit that, times negative n plus 1 plus 2n. Okay, that's 1 over n. Well, distribute the negative through. I get negative n plus 2n, that's n minus 1, like that. And now, because I've got this closed expression, I could ask, you know, way back here, well, what's the limit of this thing as n gets really, really big, right? So what is the limit as n goes to infinity of n minus 1 over n? Well, that's just the limit as n goes to, oops, infinity, infinity of n over n minus the limit as n goes to infinity of 1 over n. Well, this first one is 1, the second one is 0, so I get 1. So according to this, well, I need to move here, right? We had a lower sum, so we had the sum I equals 1 to infinity, oops, not infinity, silly me, n, I equal 1 to n of our negative 2, and that was I over n, like that, plus 2. Let's see, times 1 over n. For every n, our area was less than that. Sorry, greater than that. Okay, but then we said, well, let's take the limit as n, make that equal, less than or equal, as n goes to infinity of our sum, I equal 1 to n, of minus 2 I over n plus 2, 1 over n. Well, that limit, since each of these terms has to be less than or equal to the area, it's much like the squeeze theorem. The answer to this is also less than or equal to the area. And so I know that then 1 is less than or equal to the area. Okay, so the area is no smaller than 1. Now actually, if we run back here, right, this is what we started with. The area is 1. Okay, and so using our calculus with the limit process, we were able to get a lower bound on the area of 1 using this summation technique and then knowing how to do limits. Okay, well, upper bound. Okay, let's look at our upper bound. Now, again, for our upper bound, well, kind of didn't draw that the best in that way, but for our upper bound, you know, we're doing stuff like this. And again, see, that was x0, that was x1, x2, you know, and these go all the way to xn minus 1 and then xn. Now, so we're taking that height of the rectangle, that one, that one, that one. Okay, so we're going from 0 to n minus 1. So this is the way I would do it. Is, you see, what we want is the sum I equals 0 to n minus 1 of our function, negative 2 xi, like that, plus 2. And then again, our width is going to be 1 over n. And that is greater than or equal to the area. So let's come down here to work on this thing. So our xi, remember, you know, x sub I is just I over n. And so we started at, you know, x0 and so forth. So we have the sum I equals 0 to n minus 1 of minus 2 times our x sub I. So that was I over n. And then plus 2 and all times 1 over n. Okay, well again, we can start breaking things up and so forth. I could take a 1 over n, and then the sum I equals 0 to n minus 1 of negative 2 I over n plus 2. And this is 1 over n. Okay, and we break up our sums, and I'll factor things out at the same time. So minus 2 over n. The sum I equals 0 to n minus 1 of I. Oops, sorry. Plus, and we have our 2 times the sum I equals 0 to n minus 1 of of 1. Okay, now this we can handle it, one of two ways, but the easiest way for me anyway is to say, okay, I've got 1 over n, I've got my minus 2 over n. Now to evaluate this thing, well, remember it's of I, so what I'm doing here is since I starts at 0, I'm really adding the numbers from 1 to n minus 1. Okay. So we need to take a moment here to look at that, so I want the sum I equals 1 to n minus 1, don't need the 0, of I. Well, remember that, if I said I want the sum I equals 1 to m of I, that would be m times m plus 1 over 2. But you see, that formula, that's an m, that's an n minus 1. I need to do that as making that substitution. So that's n minus 1 times n minus 1 plus 1 all over 2. Well, I can simplify that part, so I get n times n minus 1 over 2. Okay, so we come back to this, and that sum here is n times n minus 1 over 2. And then plus, now here you have to be very careful. It would be easy to use that same logic that I'm starting at 0, that doesn't matter. Oh, it does, because it's the constant function 1. Okay, so when I add this up, how many 1s do I have there? Well, I've got 0, I've got 1, all right, up to n minus 1. Well, you see that's actually a total of n things, so that's 2n again. And so this is, again, doing some cancellation. We get a minus n plus 1, so this turns into n plus 1 over n. And so I'll go here and we'll just scoot down below that stuff. So what I want, what I've determined, I guess, is that this sum from I equals 0 to n minus 1 of minus 2 xi plus 2 all times 1 over n, that boils down to n plus 1 over n. And that's bigger than my area. Now, if I take that limit as n goes to infinity of n plus 1 over n, well, that's 1. Okay, again, by that same reason, I get n over n and 1 over n. So it goes to 1 plus 0, so that's 1 again. But that's greater than or equal to the area. So finally, after all of this, what I have is that 1 is less than the area, which is less than 1. So the area must be 1. That's, again, like the squeeze theorem idea. The area must be 1. So there is a very long and detailed look at how we can use our calculus. Okay, the calculus part is the limit stuff. To begin by approximating that area, but then using the limit, we actually can get the area as 1. Okay, so long one there, but an example of how we can use it, and in this case, to get a result we knew was right. We know that the area of that triangle is 1, and sure enough, we were able to show it this way. Okay, using limits in a simpler area of a rectangle. Okay, so that does it for that one. That is a very long one.